Okay, guys. Hi, everybody. Please open the cameras. We are starting. We got a really cool tutorial today about Lorenz and Ampere, and we actually going to talk about loudspeakers. Everybody of us has loudspeakers. It can be on the phone, right? This is how loudspeaker looks like, and you can hear music, right? You can have loudspeakers on the phone, on the monitors that we have right now in class, the microphone, the loudspeaker of your computer, and so on and so on. And the phenomena of loudspeaker really connect to two laws that we know. It's Lorenz and Ampere, Ampere law. So we have air conditioned, we have loudspeakers, and we have Lorenz and Ampere in this class. So what's going to happen? Let me draw how looks a huge magnet that actually is inside every loudspeaker that you have. So inside every loudspeaker, I'm moving to this board. Okay, inside every loudspeaker, you have kind of a cylinder looking like this, the whole cylinder. And this cylinder, so you can see that this cylinder actually have a pole. Let's fill it out, have a pole. It's a north pole. And inside the cylinder, you have a small cylinder, which have south pole. Okay, you see what I mean? Let me do it more 3D fashion, like, oh, you see what I got over there? So it's a hollow cylinder and another cylinder inside, and this you have inside your private loudspeaker. And my question to you is, let's look here. This is the question. What is the direction of the magnetic field, right? Of the magnetic field. What is the direction? So if we're looking at a bar magnet, if we have a bar magnet that you can buy in a store, we know it's divided to two poles, right? We have the north pole and the south pole, right? And how the magnetic lines curve around it. So let's do on purple. Maybe I got, let's do green. See green? Let me know if you see the green. So the lines of the magnetic fields are going in that manner. They're going from the north to the south. From the north to the south. And what I want you to notice, this is the direction of the magnetic field. Okay, it's going from the north to the south. And what I really want you to notice is how dense the lines are, okay? For example, you see here that the lines are really dense, dense line. And what does that mean? Remember, we had that also in electric field. That means that the field is actually really strong, right? So here we have a strong, this is equal to strong B, right? And once we have here, we have a space between them. You see it? This space actually means that the magnetic field is actually weak, not strong at all. Okay, so space, lines mean weak B. Okay, so the magnetic field is stronger the most where? Here and here. And it's going from north to south. So let's look at our example. So what actually the magnetic field should be like? From north to south, so it's in that direction. That's what happened inside your loudspeaker. Understood? So if we want, to be more algebraic and talking in a math language, so it's going to be really precise, we're going to do this z-axis, let's do this and this x and y. So the direction is actually radial, right? But not exactly radial, it's actually minus the radial, right? Because it's pointing inward and radial is pointing outward of the region. So the answer to that question is that B question. So B direction is actually minus the radial. Understood? Perfect. let's go to the next question. The next question is, if I'm gonna take a wire, let me put, here it is. If I'm gonna take a wire and gonna shove it inside this cylinder. Okay, let's have a 2D look on the cylinder. We have the out shell, right? We have this thing, which are a north polarity. We have the blue thing, right? Which is S. And we have the magnetic field, which pointing in the direction, agreed? Radial. And I actually shoving inside some rod, some wire. Let's do a really ugly wire inside it. This is the wire. And the wire have a current go in the direction. You see it? It's the wire. So what is the force? So B. What is the force on, I don't know, ugly wire? Ugly wire. So do you remember what was Lorenz equation? Lorenz equation was F, the force, equal to Q. You know what? Let's do not Lorenz, let's do Coulombs. Coulombs was Q multiplied by E. Remember that? Really easy. This is a vector, and this one is just amplitude. How much I'm sensitive to the electric field outside, right? So that was Coulomb equation. And right now we learn a new one, which is Lorenz law. Lorenz law, is pretty similar. It's Q multiplied by B vector, but in between them, you have extra term, which is V and a cross. You see the difference between the two equations? So this force is actually a little bit more pain in the S, right? It's similar, but it's not the same. You also need to have Q as this one. You also need to have some external electric field, or here's external magnetic fields. But it also should have what? A velocity. Which means if I don't have a velocity, this force does not affect me. If I'm a charge and I stand in place above a magnet, I don't feel it. Somebody needs to give me some velocity. And also, look at this. We have this cross. This cross actually tells us directions. Okay, so it's not enough to have charge, have a magnetic field, and have a velocity. I need to be with the velocity and the right orientation. Okay, if I got to this, if the magnetic field is going like this, and my velocity is also like this, the cross is gonna be zero. Or if I'm gonna be the other way around, because the sinus here gonna be also zero. So this diagram, okay? So we're gonna see it a lot that in magnetic fields and in electrical fields, they have a really similar, similar equations. They're gonna be kind of a rehearsal. So magnetic is actually gonna be easy for us. And sometimes, sometimes this equation easier, this hard, and sometimes the opposite. So today we're gonna see some equation that actually gets simplified by magnetics, okay? And perfect. So if we have a really ugly wire, what we're gonna do to ugly stuff? We're gonna divide them, right? So let's divide this wire to small pieces. We clean that a little bit. So we have this ugly wire, and we're gonna cut it to small pieces. We can do it, and try to understand what is the force on this one only. So I'm moving to this board, please. So let's look at the F. What is the force that actually applied on the little piece of wire? A little piece of wire in a, let's say, it's because it's a line, let's call it dF. Okay, just small piece here, right? So dF is equal to how much charge I have on this particular wire. If this is Q, this is differential on F, so you have dF equal to dQ, right? It's a small amount of charge on this part. The velocity of this charge, right? Cross B, right? The vector. Okay, let's do it more. And can we write V in a different form? You can write V, by definition, is what? Is how much this line actually moving, right? This one how fast it is. And if we look really carefully, we can see that this and this, what is it together? This is I, exactly, this is the current. So this one actually equal to I. Here I stayed with DL, which is a little piece of the wire directed in the current direction, okay, cross B, right? And this is the force, this is the total force. Not yet, we need to do the superposition principle. So F equal to sum equal to the sum of its part, right? And this one equal to what? To integral on this stuff. I is a constant for everybody, so I can take it outside of the integral. But DL cross B is stuck inside the integral, right? So that's what we have. This is the force. And what we have in the integral boundaries, this is where we start and where we end, right? Start while, start, end, right? Of the wire. We're running on the wire itself, DL, right? And then two vectors. D is from the environment, what is the magnetic field I have, and DL is a little vector that tell me I'm here on the wire, this is DL, and I'm pointing in the direction of the current. And we have a lot of DLs, and we're gonna sum them up for that. Okay, let's do it more practical, okay? Because inside the loudspeaker, you actually have some wire, okay, with the current. But this wire is actually a really simple wire, simpler than you think. Is just a circle, like a hoop. It's looking like this in a radius, specific radius R. That's all. That's the wire. So let's calculate the force for the wire. That's gonna be section C. So section C gonna be what is the force, not on a crooked wire, but on a simple wire hoop. Okay, so let me write it down. So C, okay, and what is the force on a wire curved like a hoop, right? So the equation is the force, right? Force equal to what? To the, guys, it's your time, like push it to the current, yes? We have an integral, which is DL cross B. So what really we need to do is to understand what is DL and B in order to solve it. So B is given, okay? I'm letting you know that B is given. So B is gonna be, B is a function of the radius, of the radial direction, right? How far I am from the poles. And it's gonna be some constant R divided by capital R at minus R, right? It must be on the minus R. Otherwise, it will not hold. So we know B. So what is B of the wire itself? So it's actually taking this. It's taking this and put R inside, right? So it's actually B0 minus R hat, right? That's it. Agree? This is B of R. Cool. Zoom, are you okay?
Yeah.
Perfect. So what's left for us to understand is what is DL. What we say DL is a piece of the wire. Agreed? So how you can call this piece? This is DL. What is it? We learned the radians coordinates, remember? So we can present that one as exactly R d theta. And what is the direction of this vector? Is going tangentially, right? So it's actually the tangent direction. So we got it, right? And if we right now we reveal actually what is the differential parameter that are going to run for the integral. So I'm going to start with angle 0, right? here, and I'm gonna finish after 2 pi, right? If I had many rings, maybe I should have more than 2 pi, right? But this is the case to me. So everything is ready for us to solve. We just need to do some algebraic work. We see that we have the cross, okay? First of all, I want to get rid of the cross. How are we gonna do it? We know, you know this cycle? Yes? You know this?
Yeah.
Okay, so this is a cycle from calculus 2. It means that if I'm gonna do the cross r theta, I'm gonna get z. Let's get rid of that. Theta z, I'm gonna get r. If I go the other way around, so I need to add a minus. So I have r theta, so I'm getting, I actually have, the order is really important. What I have first, I have theta, and then r. So theta, I'm going against the direction. Theta, r, so I get z, and I went in the minus direction, so I should have a minus, but I already have here a minus. So it gets plus, okay? Again, we start theta, cross out, we get z, but we went on the wrong direction, so it's minus, but we already had a minus here, so minus and minus, we're getting a plus, perfect? So the force is actually, so the force will actually, this ring actually feel a force. Somebody tried to move this ring around, okay, inside the magnet. So the force is actually equal to what? To I can take this one out, right? I can take this one out, right? And I end up with an integral of d theta 0 to pi. So I have here 2 pi. And what is the direction of the force? We already said it's gonna be at the z direction, right? So this is the force. So what's happening? Look, the ring actually want to move at the z direction. You see it? If this is the magnet outside, inside, the ring is over here, the ring want to move. Understood?
Yeah.
Great. So, any questions? Perfect. So, what I want to do now, instead of talking on one rings, let's do many rings. Do you see what I have here? Let me come to the camera. Here it is. Do you see what I have here? You see, I got many rings, right? Loop around this thing, right? Each ring actually has some force. You see it? Do you understand what I mean? So each ring actually possesses this kind of force. So my question to you is, if I had not this nice wire, like a wire that is actually loop around, let's clean this. So if we had, this is already C, right? If we had n rings, which mean we have like a solenoid shape, what would be the force on the wire, right? So F total equal to what? So what we can do, we know what?
Could you just times it by like the length?
Multiply by the length. It's the right thing to do. But look, I can do something. You're completely right. I'm gonna do the same idea. What he said, dude, your integral right now, instead of finishing start at the wire and then finish after one round, is actually has more rounds to do. That's what you say. So you actually have more line to go over, right? More DL, right? That's what he said. Makes sense. But we can look at it in an easier way. We know that the force on one ring, we're gonna get the same result. One ring is I like this. I, B, 2 pi R. And you say, dude, extend that. And I say, dude, if I know that I had n rings, eventually I'm gonna have n multiplied by this force. Understood? It's kind of the superposition principle. Okay, so we know the force. And my question to you, you see this dependency. So all this stuff actually inside the loudspeaker actually want to move, right? It's want to move in the Z direction. Want to move that way. If this is Z, want to move that way. But look what I had here. I had here the current. See it? If we're going to put here a really special current, for example, some amplitude, some magnitude, multiplied by a sinus, which means something that oscillates. How much it oscillates? 2 pi f multiplied by t. If we're going to have this function here, what's going to happen to the force? How does sinus look like? It's becoming strong and weak, strong and weak. That side to that minus side, plus side, minus side. So this shape actually gonna vibrate. It's gonna vibrate, and that's what happened in the loudspeaker. For example, if I want to do the note, musical note A, okay, or La, okay, La, okay. So what I'm gonna do, I'm gonna take this frequency to be 440 hertz, which means hertz is actually mean how much this happened in a second. So if you're gonna slap the air, just slap the air 440 times a second, you're actually gonna generate the note A. And if you do it in another frequency, you're gonna add another note. And if you do many frequencies, you're actually gonna get a symphony. Okay, so what we actually do to a loudspeaker, the computer tells the loudspeaker, hey dude, put this current inside and push the air in that manner. So, and I also made you, just for visualization, you see I made here some cone. You see this cone? So when this thing actually moving, this is sinus, let's do the sinus. The sinus actually, I'm strong, I'm going back, and now I'm minus. I'm strong plus, minus. This is the sinus, right? So all these things actually hitting, punching the air. You see this cone shape? See this cone? So this actually makes it easy to hit a lot of air, right? A lot of air to actually like punch a lot of air. So let's say that we have a cone shape inside the loudspeaker. This is the concept. Okay? So this was the question about loudspeaker. And let's draw it, okay? Because I think it's really nice and it's good to know. I really love to teach stuff that are relevant to our life. So, and also I want to teach you stuff that actually, you know, I don't know, the one that invented the loudspeaker, actually a genius. They do millions, right? It's a huge startup. So I think it's important to teach you this stuff. So we have this solenoid, you see it? And it's feel a force. This force is pushing it. This force is dependent on the time, on the current, right? And it's moving. And this one connects to a cone. And this cone actually, see, what is see? It's saying, hey, Mr. Oxygen, oxygen 2. Hey, Mr. Nitrogen, 2, oxygen 2. Hey, carbon dioxide. Hey, a lot of air. You see air, that's what this cone see. And what it do to it? It push it. You give it a force, it push it. And it push it in some frequency. This is the previous one that was pushed before. And it push all this stuff into what? Into your ear. And actually your ear is a device, not to hear sound actually, to understand how much the air get punched. That's actually what the ear is all about, okay? So this is the concept. And now I really want to focus on this, the solenoid, okay? Until now, okay, you learn there's a magnet, okay? But actually there's two types of magnets, okay? The first one is a constant magnet. That's right. Is a constant magnet, which you're all familiar. For example, the bar magnet. You have here north, you have here south, and whoop, whoop. This is a magnet, right? We have two kinds of magnets. Constant, which is stay magnetic, but we can also take a wire. This is crazy. If you take a wire and put a current inside it, what you actually see is there is a magnetic field around the wire. This is insane. So this one is called electromagnetic, electromagnet. This effect, okay? And I want you to look here in the demonstration that I brought to class. So you can see here that Earth is actually, come down here to my face, perfect. So Earth is actually a huge magnet, okay? It's a really complicated magnet. Here you have the North Pole, the South Pole, and you have a magnetic fields going around the Earth, okay? And here, you see that I have small arrows. You see down, zoom inside. It's like, dive in, dude, dive in. They're losing you. Don't, yes? More, even more. Don't be afraid. Okay, perfect. So you see that all the campuses that I put here actually pointing at the direction of the North Pole. That's what I'm actually doing, okay? And right now I'm gonna apply a current. It's gonna go through this wire. And I want you to observe really careful what's gonna happen to the campus. What's happened to them? They actually change their direction. You see that the direction changed? In what form? It's going around in a circle. Let's change the direction of the current, okay? Let's change it. Other side. Oh, what's happened? It's go to the other side. So let me explain to you what you just saw. Okay, zoom back to me. Okay, so remember that we learn in electric field, we learn two rules. Two interesting rules. We learned that the same charge, what they're doing, same charge are, guys, zoom, repel each other. Great, so they repel each other. And we also learned another rule. It's not the same one, it's a different one. That plus and minus actually what? Attract each other, right? Attract each other. So we have two different rules. And we have two different rules in magnetics, okay? What are the two different rules that we have in magnetics? The first one we already learned, which was the second right-hand rule, okay? You saw it in the previous video, that if I just gonna remind you, it's not relevant to the class, but it's important that we talked about it. If I have, let's do the other way around. If I have my hand, okay? So here, this is my hand. So V gonna point like here. Like I think about V, good for you, good that you did that, good, V like kind of thing. This is the velocity. The magnetic field, I can shoot it like a gun, okay? I can shoot it. So this is the direction of the magnetic field, B, okay? And here, this is the direction of the force, okay? So V, B, F. F, the force is actually like giving a slap. This is the same thing here, from here. So if you give somebody a slap, where's the force? Is here, right? So force, B, you can think about B, the bag, okay, that you try to shoot it. And V like, good for you. Okay, this is a method to remember. And what's really important in the exam? Not taking your right hand and right and do it with the left hand, because then all the answers are gonna be wrong, especially if it's a multiple questions, okay? So this was the second hand rule, right hand rule. Now, which cover like first rule. But now I want to teach you another rule, like we have this one. The second rule is what we just saw, is the first right hand rule. And what does it mean? It means do the like shape. Okay, you do the like shape, zoom deeper. You do the like shape, and this one, like the velocity. Remember the velocity is actually parallel to the current. We just saw it, dl, dt, right? dq, right? So this term is the velocity, right? Velocity, dl. So this term is actually equivalent, right? You understand what I mean? So V is actually where is the charge is going, right? V, it's like a current. Okay, so V is again like a current. So V, the thumb show where the current is go, and the fingers gonna curl around it, and give you these circles, the magnetic fields, okay? So let's dive back into the demonstration. So what's happened when I apply this current, I can see that they actually turn around in this manner, which means current going in this direction, and the magnetic field actually curl around this wire that way. And if I'm gonna flip the direction of the current, oh, look at that. Now it's going down, and you see how the arrows actually curves? So perfect. So right now, I want to ask you a really hard question. Okay, not that hard question, but it's really similar to this concept, but in magnetic. So let me sum up, okay? So this is not important. This was just, you know, a reference because I told you I love to view all these concepts as a parallel concept, okay? So we have this, we talked about that we have this rule, now this is a separate thing. We have the second hand rule, and we have also what? The first right hand rule, which said this is V or I, the current, and you know the magnetic fields. Let's do it more precisely. And the magnetic field actually gonna curl around the wire. You see it? Understand the concept? So my question to you, now that you understand this concept, let's see you in action. Let's say that I have two wires, okay? Pointing at your face, okay? Two wires. What is the magnetic field in space? Let's try to do, okay? So let me clean. So let me clean that. So if I have two wires, let's say infinite, it doesn't matter, two wires. This is section F. What is the magnetic direction for two parallel wires? Okay, that's a question. So let's draw two wires. Let's do here. First one. This is the first one, right? Wire going from here to that. And let's do other one right here. Two parallel wires. See them? Okay, so what's actually the magnetic field this one produces? Taking my thumb, I put it in the direction of I, said it's coming toward your face, and I can draw this circle. So draw this circle. Oh. So in which direction? Like the fingers. This is the direction of B. So let's do the other one. Oh. So in this direction, direction is the same. It's going here. Like this is called counterclockwise. You see? Counterclockwise. So what I see that's going on here at this point, one is coming in and one is coming out. You see it? So at this point, what do I expect it to be? The magnetic field? Zero, because this contribution, sorry, the blue contribution actually cancel out with this one. So you're not gonna be any magnetic field at that direction. You see it? The direction, the magnetic field. Got it? Perfect. So let's draw another line with a different radius. Let's do a bigger radius. Let's do a new drawing, same these two. And now we're gonna do this, a bigger circle, a bigger circle. Let's see what's going on at that point. So they're again going in the direction, all of them going like my fingers asked me to do, obey me to do, which is in my case counterclockwise side, right? So what's going on here? This one said, let's do the magnetic here. And here, let's do the magnetic here. And the purple one said, dude, I'm coming from another side of the world, and I prefer it to be like this, and here to be like this. So what we actually see here, interesting pattern. We see that actually the summation of them, what's gonna be? at the direction, you see? On top of the wire, the direction gonna be like this. And down below, it's gonna be like this. So, and here, you know, the effect of this one is weak. So we can actually it's gonna follow this pattern. And here, it's gonna follow this pattern. See? So this is actually the magnetic field. Let's do a new drawing. So what is the magnetic field of the two of them? Just, you know, directions, thinking. So this one and this one, actually gonna do this. Here they're gonna point at the direction. Here they're gonna point at the direction. Here they're gonna curl. Here they're gonna curl. You see? You understand the concept. And it's really similar to the concept of, you know, we had this thing. Thank you, cameraman. We have this thing, we have this thing, you know, and here the charge is pushing. So the electric field is going that way. So it's the same idea, it's the same concept. You see it? Right? Perfect. So now when we did this, I want to go back to my real question, which was that. What is solenoid? So let's draw the solenoid. So the solenoid that we have inside our loudspeaker actually looking like this, right? And I have a lot of this, and this length is L, and the radius is R, and I'm letting you know that in my case, L is much, 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 much bigger than R, which means I have a lot of coils, L is really long, and R, and I want you also to see that if you look at that perspective, right, this is the solenoid, what you see? You see that this line actually looks the same as that line, as that line, as that line, as that line, which means if I'm gonna stand here and gonna look somewhere, everything gonna look the same, you agree? Which means we have a symmetry, right? Remember what we did in electrical field when we had a symmetry? Which tool did we have? We had Gauss's law, remember? So right now I'm gonna teach you Ampere's law, which is the parallel one to the magnetic. And you know what's super cool? Ampere is way more easy than Gauss's law because we're gonna do a small, we're gonna decrease the dimensional. Gauss's was 3D, Ampere is 2D, simpler. So let's do that. Let's do the symmetry, okay? But before that, I want to use the same intuition that we had here. If I'm going to cut the cylinder, shock, like this, what I'm going to see? I'm going to see wires going like that, right? Right, this is the cylinder coming at me. And down below, what I'm going to see? Going like this, right? You see it? So what's going to be the magnetic field? Okay, this is what is the direction? A, B, C, D, E, F, G. What is the direction of the magnetic field? Okay, so we know from the previous one that each two gonna produce this kind of thing, right? This one, and this is gonna do this, right? So they're gonna continue doing this, the upper part, until the end. Gonna go like this. By intuition, by the right hand rule. What's gonna go down below? Down below, the X direction actually. So if this is X, which means I see the tail of the arrow, which means the current go inside. So this one gonna do that. And this one gonna do that. So actually it's kind of like this. You see it? You see this pattern? So I want to ask you a question. What's going to go in the inside? What they're going to do? Sum up, right? What's it going to do the outside? Look, this term actually goes all the way also to here. So they're going to cancel outside. So we actually ending up with this thing. We're getting a strong magnetic field inside, this one, a strong magnetic field inside, and a really weak one outside. Really weak one outside. Oh. You see what we have? What I said that the line spacing mean? Strength, right? So that's what you actually have when you do a cylinder. And this reminds me what? A capacitor. Remember capacitor? Plus and minus. Here we had a huge electric field. And what we had outside? Nothing, right? It's the same concept in the magnetic perspective, okay? So right now I want to teach you Ampere's law. And Ampere law is really simple to teach if you understand Gauss's law. So let's do Gauss's law here. So Gauss's law, remember Gauss's law, what does he say? He said, do a closed integral, on the electric field dA, right? This is the end. And here what we need to do, we need to choose a volume, right? Let's do a volume. We need to choose a volume and we need to sum what? The area, right? The area, dA, this one. We need to sum the dot product between dA and the electric field. Remember? That's what we need to do. It was a 2D integral, right? Right? It was a volume, but we really care about the outer shell, right? About the surface. And now I'm gonna draw Ampere's. Are you ready? Ampere is looking at this. It's doing a line integral, not the surface, a line, which means I want you to walk on some line, okay? Imaginary line. Like here we have an imaginary box or sphere, imaginary. I want you to find imaginary line. Let's do a heart. That's how I like to do it. I do a heart, okay? And walk on the path, dL, the path of the line. Like we had dA, remember? The area unit. Now we have dL, which is the line. So, and put here the magnetic field, dot product, dL. Do you understand what I did here? So this is a volume, agree. Like this one is what? An area, right? This one is an area, right? Understand they are similar? And what this one was equal to? You know what? Let's do that. Let's do that. Let's try to find the magnetic field of the solenoid. Okay, let's do it. So I'm gonna choose. This is gonna be my solenoid picture. So I'm gonna choose a line. I need to do some line. Whatever I want, whatever path that I want, but I want it to be a line. Actually, I need it to be what? A loop, a closed loop. I need to be a line which starts somewhere and ends somewhere, right? And not somewhere, and in the same place, because it's a closed. Like Gauss was a closed surface, remember? Now it needs to be a closed line. What is a closed line? For example, I need a rope, some rope. Oh, let's take this. Okay, perfect. So that's, not a good wire. So, okay, so imagine that I have some headphones or something. So I got a wire, some loop, but it needs to what? Finish at some point together. So I'm gonna choose this one, really complicated one. Are you ready? Hop, 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 hop. That's the path that I choose. Let's choose direction. DL gonna be pointing that direction. That's the direction. This is each one of them is a DL going in that direction. Like in Gauss, we can do this. Right, we can do, I choose this thing and I choose this dA, right, dA. The same concept. You see it? Perfect. So what this one equal to? E of this square B dot dL. What is it? So like we took the faces out of the cube, you remember we in Gauss's we took the faces out and we calculate, we can actually do the same thing here. Instead of the faces, we can split what? The edges of the loop, right? We can split them apart. Everything is clear, guys? I think it's super complicated, but I think we're doing fine. Are you with me? Yes? Good. Okay? So this is super important. So we're gonna take these edges, okay? So let's split it. So I got this one, right? The inside one. Let's give it dimensions, right? Let's call this H, these dimensions. and this is gonna be L. Okay? Perfect. Yes, you got it? L and L. Good. So let's do this one. So this is DL, right? And it's going that direction. So here we actually have integral of B dl. You can see it's big enough. Integral B dl, which start at 0, end at H, right? From here to here. And what is the dot product between them? Is 0, which means, sorry, is 1, because the angle, the magnetic field pointing that way, and the loop pointing that way. The same thing we had here, remember in Gauss that we have E, and we have the dot product between them? So what's gonna be a good choice of a loop? A good choice that actually give you a nice dot product, a nice dot product. That's what you want to loop when you want imaginary loop, okay? So BDA, so I can actually do it simpler. The multiplication, the B is gonna be some value, the B in, I don't know what is it, but it's B in, inside the solenoid. And the dot product gonna be 1. So it's actually gonna end up to be L, right? See it? Okay, let me understand what we said is gonna happen here. This B, I don't know, it's a crazy B. It's going like this one is going like this one is going like this, I don't know. Two things. First of all, you see that the angle between them is what? Is almost 90 degrees, first of all, which kill the edge. And also, what we said outside happening, the magnetic field is what? It's not 0, but it's weak. It's really weak. So B in, sorry, is much larger than B out. So if I have B in my equation, B out is gonna die, right? It's not that important. So we actually, when I go in this direction, actually have 0. You see it? And now I go into this edge. And what do I have? I have B out, right? This is, we said the magnetic field is going in that direction. The angle between them is what? Is 0, which means the cosine of the dot product is 1. So it's actually multiplied by L, right? And then we have this magnetic field, right, here, and this DL. But what we said, that the angle, sorry, I didn't draw it right, but the angle between them, the solenoid is really long. The solenoid is really, really long. Sorry about that. So this line is actually curved in a almost 90-degree fashion, but it's also outside. So also the 90 degrees, also really weak. So these two terms actually dying out. And what we said before, that B out is really small compared to B in. So I can neglect this term. So I end up, okay, that the right-hand side of Ampere's law, the right-hand side is actually equal to what? To be inside multiplied by the length of the loop. It's an imaginary loop. It's not a real loop. It's inside my head. Okay, imaginary loop that I decided to be in a distance L, and I see that H doesn't matter, is dying out anyhow. Okay, let's back to Gauss. Cameraman, follow me. This is really good part. Okay, so what actually we had here in Gauss's law, remember what we had? Okay, also you can use 1/epsilon, right? Okay, and what we have here? Q in A, which means what is the charge that live inside this volume, okay? For example, if I choose my imaginary dimension, my imaginary shape to be watermelon, so how much grains that I have inside this watermelon? This is the charge. I care only about the one inside. So we have something really similar here. Remember that we had, we had Coulomb force, we had QE, right? And then we have Lorenz force. What actually was caring about? Q V cross V. We're actually caring about moving charge. Moving charge is actually what? Current, right? Moving charge, I have charge and it starts to move, migrate to some places. This is a current actually. This is the definition of current. So here I expect to see something that behaves like a current. So here actually what I see another constant, a magnetic constant, which called the permeability, okay, the name of it. vacuum of space, permeability of space, multiplied by, let's do the sum of charge, the sum of currents, pen from the word penetrate, okay? Or from the word poke. That's how I like to think about it, penetrate or poke. So what is this current? So as we said before, this Q in presents what the charge that's wrapped inside this volume. But here, it's actually the current that penetrates this area. You understand what is here? Actually, we're getting simplified idea. Instead of to be a charge inside the volume, I'm a current that tries to poke this area. For example, if I'm gonna have some frame and I'm gonna put it inside water with soap, I'm gonna put it out. This frame can be a loop, and this soap bubble actually is the area. And if I would try to poke it, this is the current that I care about. I don't care if there's a current here, current above me, under me. I just care about the current that actually try to penetrate this imaginary area. So please answer me. I'm going to clean this one. I'm going to clean all this, stuff. We have just, they're going to draw. No, okay. I'm going to do it from all over again. Draw with me another one. So if this was my cylinder, of solenoid, not cylinder, sorry, solenoid, and I choose this loop, how many currents actually poking this area? How many? 1, 2, 3, yeah, 4, but it's just a schematic, right? So I said it's length L, right? Length L, and I know that the length of all the solenoid is big L, capital L, right? So here, a camera with me, can you follow me? Okay, so this term actually equal to this one, which is mu0 multiplied by sum of poke or penetrate current. And in my case, I have total, how many loops I have? Capital N, remember? Capital N was the number of loops that I have. So here I have N, and I need some correction factor, right? Because I don't have all the loops. I have some L divided by L. This is a fraction correction, right? What I did over there, I said, dude, I have only this Rashi. For example, if L was a half, L was, I don't know, half of the size of L. So I have half of all the loops, right? If it was a third, so a third of all the loops, right? So this fraction actually taking care of how much of the loops I actually taking, okay? Is how much area my imaginary loop actually taking from the whole solenoid. This is the 100%. This is how much I do it. Clear? Perfect. So what we have here, so let's clean this. So we have the two sides of the equation. You understand that we have V in multiplied by L equal to what? To mu0 in L divided by L. This dying out. Hey, dude, this is my imaginary length. It's dying out. I can choose any length that I wanted. It would work, okay? So V inside the solenoid actually equal to mu0 N divided by L. Something is missing. UN L. Wait. And I, the current, sorry. We forgot to put the current. Each loop have a current, right? We're summing up the currents. This is how much we summing. So we have your I, we have your I. Sorry about that, okay? And this is really, really important equation. Like we had in a capacitor. Remember that we have two plates. Let me clean the board. We have two plates. And we have this, right? This is the first place, this is the second. So that's clearer. We have capacitor, this and this plus, this minus. So the electric field inside is what? Is sigma divided by epsilon, right? Remember? This is the equation, or I have it too. This is the equation, right? So we have this, so in magnetic fields, and this was inside. So the solenoid is the equivalent idea of capacitor. Okay? This is a way to actually have magnetic energy preserved. For example, if I have a capacitor, I can put a lot of electric field inside, keep that safe, it uses whatever I want. In magnetic fields, we have the solenoid. The solenoid is actually holding a lot of magnetic field. Let's go in here. Come here. Okay. So here I brought another demonstration of a solenoid. A really stupid solenoid. And here, come. I have a really stupid zoom, really zoom. Yes, it's more to this table. This. Zoom as much as you can. Or more. You can do it. I trust in you. Go a little bit up. Yes, zoom more. This is the max. Okay, guys. So look at here. So this is a solenoid, a really stupid solenoid, as I told you before. Why is it stupid solenoid? Because it don't have a lot of loops. So the effect is gonna be even weaker than what I really wanted to do. So I'm gonna put here this iron, which is kind of, you know, sensitive to the magnetic field. Okay, I'm gonna put it here. Oh, sorry. I'm gonna put it here. And what I wanted to see is how the magnetic field is oriented. So now I turn it on, okay? So what do we have here? You see that the lines of the strong magnetic field obey the law. There's a strong magnetic field inside. I can't control myself. I'm going in that direction. That's what they're pointing at. And really close to the wire, there's also magnetic field. You see a lot of loops. But here, nothing. I don't care about you. Here, nothing. I don't care about you. It don't interest me at all. Okay? So now I close it. Oh, take it off. Here. Okay. So come back to me. Guys, we almost finished. Okay? So just a summary. So what we had today, we talked about Lorenz force. We finished talking about Lorenz force, and we start talking about Ampere force, which is equivalent to Gauss's law. But you also need to learn Biot-Savart. Biot-Savart is the equivalent to Coulomb's law, to this one. K, Q1, Q2 divided by the distance squared. Remember this thing? So you have also this one, the equivalent one, and you have it on the YouTube tutorial, the next one. So follow that one. And I want to understand, we each time gonna have some parallel idea to the one we have in electricity, right? Magnetism is parallel. We have Lorenz, we had Coulomb, we had Ampere, we had Gauss, we have the right-hand rule, we have plus and minus repel, attract, right? So that's what I want you to take from here. And remember this formula of the solenoid. It was a pleasure to have you. Thanks to the people that come to the class and the people that follow us on Zoom and open the camera. And see you next week. Okay, guys, and good luck. And if you have any question, go and don't be afraid to stop me and ask questions. Thank you.
Thanks, Ron. Bye.
Bye-bye.